Hello everyone. In this video I want to talk about impedance matching. So let's suppose you have a load that you want to drive, and this load has value RL, and you have a transmission line with characteristic impedance Z0, which you will use to transmit the signal into this load. Now, of course the load cannot be changed, so we have to do something in order to match the impedance of the line to the impedance of the load. And of course you cannot just change the load, you have to find another way. So this method of matching the impedance is called the quarter wavelength transformer method. So what we do here is we separate the transmission line from the load, and in between the path we put another transmission line which has a total length x equal to lambda over 4. So lambda over 4, and lambda is the wavelength of your signal. So remember that lambda times the frequency is equal to propagation velocity. And so if you know the frequency of your signal, you know the wavelength. So the first thing that this requires is a length of transmission line equal to lambda over 4. And the second requirement is we need to find a characteristic impedance Z1 for this line, that this line has to have in order for this matching to work. Now remember that for every transmission line we can find the input impedance at any point on the line. So what we're trying to do here is to find the value Z1, so that the input impedance looking into here is equal to Z0. If that's the case, then this transmission line here will see an input impedance of Z0 and everything will be matched. Excuse me. So how do we do this? Remember that the formula for the input impedance is equal to Zin equals Z0 times ZL plus J Z0 times tangent of beta x divided by Z0 plus J ZL times tangent of beta x. And now the point here is if beta is equal to 2 pi over lambda, and x is equal to lambda over 4, because this is the length of the line. So beta x will be equal to 2 pi over lambda times lambda over 4, which is equal to pi over 2. And this is good because tangent of pi over 2 is infinity, and if that's the case, then this term right here will be infinity, and so will this one, and so this term right here does not matter, and this term does not matter. So the formula will be Zin is equal to Z0 times J Z0 tangent of beta x divided by J ZL tangent of beta x. And so of course this J cancels with this J, and this tangent cancels with this tangent, so the formula will be equal to Z0 squared divided by ZL. This is the input impedance looking into right there. So remember, we are trying to find the characteristic impedance Z1, and so in this formula here, this Z0 becomes Z1, and the input impedance that we are looking for is Z0. So this means that Z0 is equal to Z1 squared times ZL, and so Z1 squared is equal to I apologize, this formula here is actually Z0 is equal to Z1 squared divided by ZL, not times ZL. So this means that Z1 squared is equal to Z0 times ZL, and so Z1 is equal to the square root of Z0 times ZL. So this is the characteristic impedance that we need this line here to have, so that the impedance is matched. So this is Z0 times ZL, just like we have here. And so if that's the case, then the input impedance looking into here will be equal to Z0, and everything will be matched. So this is the first method of matching a transmission line. And one requirement for this method is that this load here has to be purely resistive. It cannot have capacitive or inductive components. There is another method which is called the stub method, in which we attach another transmission line here parallel to the first one, so that with the ends shorted, and that will help us match the load as well. So I'll see you in the next video.